Welcome to Lab 5 on Faraday's Law. Let's get started. So in this lab, we're going to be dropping a bar magnet into a conductive tube to see how its behavior changes. The idea is that a bar magnet moving through a conductive tube is going to induce a current, and that current produces a force on the magnet. We're then going to be creating a computer simulation of this through GlowScript to see how our experimental data compares with a simulation. The major principles in this are Faraday's law. That helps us find the current induced on the tube by the falling magnet. We have the Biot-Savart law again. That's going to help us with the magnetic field that's exerted on the tinfoil. And then Newton's second and third laws. That's going to help us look at the forces later on and make some pretty interesting conclusions about this. So here's our experimental setup. We have our conductive tube. We have all of our associated measurements that we're going to need for our simulation. And basically what we do is we drop the magnet inside of there. Now, what we notice is that dropping the magnet inside of this conductive tube yields a longer fall time than just dropping it outside of anything else and just letting gravity affect it. So the average fall time that we found was 0.882 seconds. Next, we're going to simulate this through GlowScript and see how this result compares with a calculation. So now we're going to take a look at the GlowScript portion of things. In the top left picture, you see our reused function from Lab 3. And that's going to help us find our dipole moment given the distance r and magnetic field B. And then below that is going to be the way that we find our change in flux over change of time for each ring of the tube. The idea is we have a bunch of stacked rings, and combined together, they produce a tube to simulate our conductive tube. So these are some other details from our simulation. In the top left, we're just calculating the current that is induced by the falling magnet. And then in the middle is kind of our big chunk of things being done. As the magnet moves through each ring, we are calculating the magnetic force that is produced, and then we are summing that along the entire length of this tube so that each ring subbed along the length of the tube produces a simulation of our conductive tube. And then our last step is just to find the net force, which is, in our simulation at least, the only forces acting on it are the force from the magnet and the force of gravity. And here's a quick peek at our results in GlowScript. So the model is shown on the left, and then we have a graph of velocity versus time. And we're going to dive into more of what all this means later. But a key thing to notice is look at the behavior of the velocity versus time graph. Should the magnet just be influenced by the force of gravity, this graph should just have a constant slope, indicating that it is experiencing a constant acceleration. In this case, the velocity versus time shows no acceleration. The slope of it is 0. So we're going to dive into that later. So as I just mentioned, because there is a slope of 0, this shows that there is no acceleration, which also, from Newton's second law, shows that the net force is 0. So in this simulation, as the magnet is falling, it is not experiencing any force, so it's not falling any quicker. The velocity is staying constant. Another thing to take note is that the color is red, so just looking at the right-hand rule, we can find that the red is indicating a clockwise current induced on the tube, and blue indicates a counterclockwise current. And one thing that we tried is flipping the magnet, and it results in basically the same motion of the magnet, however, it changes the direction of the current. So instead of it moving clockwise in our simulation, it moves counterclockwise. And now we can look at the kind of interesting part, how our experimental data looks in comparison to our simulation. So in our experiment, we found an average time of 0.882 seconds. In our simulation, we calculated 0.934 seconds. That's an error of 5.57%, which is not too big compared to some of our other experiments. There are obviously forms of error in this. The simplicity of the simulation, we're not taking into account air resistance, deformities of material. We're assuming we're dropping the magnet directly in the middle of the tube, etc. And the lack of measurement precision. Just recording on a smartphone and counting frames is not the most precise form of measurement, but it is pretty good for making an approximation. And we'll take a look at some quick finishing questions. What if the resistivity of our conductor were reduced as close as possible to 0? So since our EMF is the product of current and resistance, reducing this current as close to possible to 0 would cause a sharp increase in the induced current. Now, as a result, the magnet would fall significantly slower because the force pushing up against the magnet due to the induced current would be stronger. Next question, what if holes or slots were added to the tube? So the number of rings would be smaller, and that would yield a slightly weaker induced current, and the magnet would fall slightly faster because the force pushing up on it would be less. Thanks for watching, y'all.